Okay, so we are actually moving into the second portion of 1.2, and we are talking about the algebraic techniques of evaluating limits, and some of the material that we're covering here will be covered live in class, and the more common, simpler techniques will be covered in this video. So you'll need to make sure that you take care of these in your notes first, and we'll cover the others in class. So here at the bottom of page 7, it says that in order to find the limits algebraically, what we want to do is evaluate the limit using direct substitution first. So whenever you are evaluating a limit, your ultimate goal is to make an attempt to use direct substitution first, and if it doesn't work, then you need to take a look at what's happening in the problem and what would be the best method to eliminate the issue, and then again go back to using direct substitution. So if you use direct substitution and you get what's known as an indeterminate value, okay, or an indeterminate form, which is 0 over 0 or infinity over infinity, or you could have negative infinity over negative infinity, negative infinity over positive infinity, and the reciprocal of this. What you want to do is eliminate that issue and then solve algebraically. So whenever you're given a problem, it won't tell you solve this by using direct substitution, solve this by factoring. You need to use your prerequisite skills for this class to determine the best method. So here for direct substitution, when you're given this problem, the limit as x approaches 1 of this polynomial, first of all, something that you need to know from algebra is that a polynomial, or in this case a quadratic, has a domain of negative infinity to positive infinity. So if I use direct substitution where I let x be equal to 1 and I plug in 1, so I evaluate f of 1, we have 4 times 1 squared minus 10 times 1 plus 3. What we're looking for here is just to get an answer. So what we get is 4 minus 10, which is negative 6, plus 3, which would be negative 3. So we end up with the limit as x approaches 1 of f of x being equal to negative 3. This is defined, so this is your answer. So these are the best and easiest problems to do. But when I take a look at number 2, when you try direct substitution first and you say, okay, let x equal 1, you have 1 squared, which is 1, minus 6 times 1, which is 6 plus 5, over 1 minus 1, you end up with negative 5 over, that's 0, because this becomes negative 5 plus 5, so we have 0 over 0, which is an indeterminate value. So once you get an indeterminate value, you need to use your prerequisite skills to determine, okay, if I factor this, maybe it will go away, which is why this is solving by factoring. So you leave the limit here as x approaches 1, and we're going to factor the top, which in this case would be x minus 1 times x minus 5 over x minus 1. So in this case, what we end up doing is canceling out the x minus 1s, okay, and then you're left with the limit as x approaches 1 of x minus 5. So you notice here I left the limit because I have still yet to take the limit. You must leave this in here. You cannot eliminate it. So now I'm going to try direct substitution where x is equal to 1, and I end up with 1 minus 5, so this is negative 4. So there's your answer, negative 4. And basically what happens here is once you cancel out this x minus 1, you're left with a linear function. And basically what you have is a hole at x equals 1. So you notice here these common factors, you have a hole where x is equal to 1. So that is another method. So now we're going to move to the top of page 8 and take a look at a couple more. So I want you to make note at the very top. It says, remember that the limit does not drop until you use direct substitution. Okay? So you need to keep that limit in there. If you get rid of it before you even take the limit, this is no longer a limit problem and it'll be incorrect. Okay, so our next method here is rationalizing. So in the past, in pre-calc honors, you were told to rationalize the denominator, meaning no radicals in the denominator. So in this case, what we want to do, if we use direct substitution, so we're going to try this quickly with direct substitution where x is equal to 0 in this case, you end up with the square root of 2 plus 0, which is the square root of 2, minus the square root of 2 over 0, so this is 0 over 0, so we can't do that. So this is considered indeterminate. So what we have to do is rationalize, meaning we want to put the radical in the denominator and we want to multiply by the conjugate of the numerator. So what we have is the limit as x approaches 0, this is my original problem, square root of 2 plus x minus the square root of 2 over x, and we're going to multiply by the conjugate of the numerator. So it's the square root of 2 plus x plus the square root of 2 over itself. Okay, so now we have the limit as x approaches 0. Notice the limit is still there. And I'm going to multiply the numerator. So when you multiply the square root of 2 plus x times the square root of 2 plus x, you're left with 2 plus x. And then negative square root of 2 times the positive square root of 2 is going to be minus 2. And in the denominator, do not distribute, just leave it. So you're going to have the x on the outside, and then the square root of 2 plus x plus the square root of 2. Now, up here, the issue is that not only did I get a 0 in the numerator, but once I used direct substitution, I had a 0 in the denominator. Remember, you can have a 0 in the top, but when you have a 0 in the bottom, it's either undefined or indeterminate. So we want to get rid of this x. If you look here, these two go away, and we're left with the limit as x approaches 0 of x over x times this conjugate. So now what that allows me to do is cancel out this x, and when I rewrite this, hopefully I can use direct substitution. So you're left with 1 over the square root of 2 plus x plus the square root of 2. Now, we got rid of the x, which was the problem. We're going to try direct substitution. So we have direct substitution where x is equal to 0, 1 over the square root of 2 plus 0 plus the square root of 2, which is 1 over 2 square root of 2. Now the good news is you've made it to calculus. You no longer have to rationalize the denominator. It's not wrong if you do, but it's one less step that you have to take. So that is rationalizing the numerator or the denominator. Okay, in this fourth problem, we have a complex fraction. So before we do anything, this is actually two problems in one. This is a complex fraction and factoring. So this is a double whammy. So the first thing you definitely do is if you try direct substitution, I'll do it down here where x is equal to 1, you're left with 1 over 1 minus 1 over 1 over 1 minus 1. I'm hoping that you can see that this is equal to 0 over 0, so I can't do it. Okay, so I'm just going to put this off to the side. Okay, so what we need to do is multiply by the common denominator to get rid of the complex fraction. And in this case, the common denominator in the top and in the bottom overall is x. So we're going to multiply by x over x. So what we get is the limit as x approaches 1. And when we distribute, this goes here, so 1 over x times x is just 1 minus x times x, which is x squared. And you notice this is a difference of squares, I hope, over x times 1 over x is 1 minus 1 times x, which is just x. So now here, if we were to try to use direct substitution, you can already see that it's not going to work because this would be 1 minus 1 over 1 minus 1. Again, still indeterminate, so we have to factor. So then what we have is the limit as x approaches 1 of 1 minus x times 1 plus x over 1 minus x. So now, just as we saw on the previous page, we have this common factor here that I can get rid of. So when I do that, I'm left with the limit as x approaches 1 of 1 plus x. So now you want to try direct substitution where x is equal to 1, and when you do that you get 1 plus 1, which is equal to 2. So this is your answer. Okay, so in this case we actually had two pieces. We had to simplify the complex fraction and we had to factor. Okay, in this last problem we're going to cover a very simple piecewise function. Okay, and what you have here is the limit as x approaches 3 of a given function, and then they define the function. So in this function, it's saying that for any value greater than or equal to 3, you're using a parabola, and the function will be linear for any value less than 3. So first of all, we need to review our definition of a limit. So this is a definition of a limit, okay? It is the limit as x approaches a from the left of f of x being equal to the limit as x approaches a from the right of f of x, and these are both equal to L. So if they're both equal to L, then the overall limit as x approaches a of f of x is equal to L. So what you have to look at here is, if you're evaluating the limit as x approaches 3, you need to evaluate from one side and the other side. So I'll follow the definition. We want to evaluate the limit as x approaches 3 from the left of f of x, which is going to be this function right here. So I'm going to highlight this in a different color. Okay, so we're going to use, in blue, we're going to use this one, which is equal to 6x minus 4. So what that means is, when we're coming from the left, we're going to plug 3 into 6x minus 4. And when we use direct substitution, where x is equal to 3, we end up with 14. Okay, so there you go. That's evaluating from the left. So that's the first part of the definition. Then we need to evaluate from the right. So we have the limit as x approaches 3 from the right, and I'll just put this in right away. This is x squared. So using direct substitution, where x is equal to 3, we end up with 9. Okay, so here's this one. This is from the right, and we're equal to 9. So what's happening here, as we approach from the left, I'm getting one value. I'm up at 14. When I'm approaching from the right, I'm at 9. So the problem is that the graph is not meeting up. So they're both not equal to the same L value that we said. So what we say is here, the limit as x approaches 3 of f of x does not exist. Okay, remember those values based on the definition must be the same. You must test from both sides.